This video is brought to you by our animation studio, Throttle. We are an animation studio run by engineers and help engineering companies to communicate how their products work with beautiful animations. If that's something you need help with, reach out with the link in the description. Late on a spring evening, 1992, the Endeavour space shuttle, on its maiden flight, stood on its launch pad in Cape Canaveral, Florida. The crew sitting aboard, ready to take on a daring mission. A rendezvous between two spacecraft in orbit, a rescue mission. Bruce Melnick was aboard that day.
The challenge we had was that this satellite was never supposed to be touched by human hands once it got in orbit. It was supposed to be way up in geosynchronous orbit, over 22,000 miles up. But it launched on an unmanned rocket that failed to fire second stage and send it on its way. So it was stuck in a useless 800-mile high orbit.
Melnick and his crewmates were about to take the ride of their life to rescue the satellite, to grab it with their bare hands and attach a new second stage. But before that could happen, a complicated series of events was about to take place beneath them. 3 liquid fuel rocket engines were about to burst into life with furious power that would tilt the entire structure off axis, held back by just 8 explosive bolts, fed with turbopumps driving fuel out of the external fuel tank slung underneath the orbiter. Meanwhile, the 2 massive solid rocket boosters lay dormant, the 2 largest solid rockets ever made to date. And when the signal that the orbiter's engines were up to the challenge arrived, an inferno would be lit inside them, causing the entire column of solid rocket fuel inside to erupt, lifting the revolutionary, reusable space plane off the ground and to orbit. This is the insane engineering of the space shuttle. We are mere minutes away from launch. Helium and nitrogen have purged the main engines. The flight surfaces and main engine gimbals have been tested. The shuttle is now fully fueled and under its own power, no longer connected to the launch pad. 10 seconds are left. Sparkler-like igniters fire underneath the engine to burn any stray hydrogen as the shuttle prepares to open the main fuel valve. Liquid hydrogen begins to race through the fuel lines, pushed by the pressure of the tanks, through the engine nozzles, where it begins to expand and turn into gas. This gaseous hydrogen drives a low-pressure turbopump turbine, elevating the rate of flow of hydrogen through the fuel lines. This is all happening in the blink of an eye. Less than a second later, the main oxidizer valves open, unlocking the fuel's true power. Fuel and oxygen meet in the 2 high-pressure turbopumps, raising flow rates even higher. Back in the nozzle, we see our first flames. Oxygen levels are still low, and combustion instabilities cause the engines to rattle. But the engine is now ready to enter its next stage, entering open-loop engine control, no longer controlled by a pre-scripted startup sequence. Instead, the engine constantly monitors pressure readings and adjusts valves accordingly. The engine begins to throttle up, oxygen valves continually opening wider. The flame transitions from a low-pressure orange flame to an eerie hot blue. The space shuttle is unique in that these engines are not directly under the fuel tanks. The expensive rocket engines were attached to the reusable shuttle, not the expendable external tank.
And because the main engines are offset from the solid rocket boosters, which are holding you to the pad, when we light off the main engines at 7 seconds, it actually bends that stack over, and you can feel this little lurching back and forth. NASA calls it twang. It's kind of a real technical term.
The only thing stopping the entire shuttle from tipping over at this point are the hold-down posts attached to the solid rocket boosters, which for now lay dormant, waiting for the signal to ignite. The pressure inside the diverging nozzle is still lower than atmospheric pressure, and as a result, we can see a flow separation layer, which gradually creeps to the edge of the nozzle as the pressure inside increases. 3 seconds until launch. The engines are checked to ensure they are running at 90% of their rated thrust. The time has come for the solid rocket boosters to ignite. The solid rocket boosters are 45 meters long and are filled to the brim with solid rocket fuel, a rubbery mixture that combines both the fuel and oxidizer into one solid material. The oxidizer, ammonium perchlorate, makes up nearly 70% of the mixture, while 16% was the aluminium fuel. We need a way to ignite the entire column quickly. The igniter itself was essentially a miniature solid rocket motor, which itself was ignited by an even smaller miniature solid rocket motor. To ensure extremely quick combustion, this main igniter was shaped with a 40-point star orifice. When it comes to solid rocket motors, the more surface area available to burn, the quicker it will burn, rapidly producing the heat and pressure needed to ignite the entire column of solid propellant. Once this happened, there was no turning back, so there were several safety mechanisms in the arming sequence to prevent it happening accidentally. The first part of the arming sequence began when technicians accessed the safety and arming device in the top skirt of the solid rocket booster here to remove a pin. This pin locked a safety device in place, preventing it from rotating into an armed position by accident. When it was rotated into position on command at T-5 minutes, it connected a standard NASA detonator through a tunnel to the igniter system. When it fires, it begins the rapid chain of events that brings the space shuttle to its highest thrust. But the entire rocket is still anchored to the launch pad, held down by the hold-down posts, 4 on each solid rocket booster. These hold-down posts anchor the solid rockets to the ground through the aft skirt, with massive 711mm long and 88mm wide bolts. The lower side of the bolt is tensioned using a regular nut, while the upper nut is a special kind of explosive nut, a frangible nut. On 2 occasions, 2 of these frangible nuts did not fracture correctly, something NASA described as stud hang-ups. These issues did not stop the space shuttle from taking off. With the power of 2 solid rocket boosters and 3 main engines, 1 or 2 improperly fractured nuts were not going to stop the space shuttle from taking off. These hold-down posts were primarily designed to prevent the space shuttle from tipping over while the 3 main engines were brought up to full throttle, or simply by a gust of wind. However, if 4 or more of these stud hang-ups occurred, the issue could have been mission critical. And so, a redesign was introduced for STS-126, where a crossover assembly was included. This new system linked the 2 pyrotechnic charges in each nut to ensure they detonated within 50 microseconds of each other. A delay of up to 250 microseconds was possible with the previous design, and this was identified as the main issue causing the so-called stud hang-ups. The shuttle is now free, with the largest and most powerful solid rockets ever used in human spaceflight powering it upwards. Each of the solid rocket boosters provided 13,000 kilonewtons of thrust each, nearly double that of the Falcon 9 first stage. But the very notion of using solid rocket boosters for a crewed space shuttle was initially met with extreme concern. Using solid rocket boosters for human spaceflight had never been attempted before. They were nearly exclusively used for military use. Like the Minuteman ICBM, the solid rocket fuel allowed them to stand ready, available to launch in a moment's notice. However, once ignited, there is little that can be done to stop them. The entire column of propellant is ignited at once. There are no pumps or valves that can lower the fuel and oxidizer being delivered. Once ignited, they stay ignited until all of the propellant is expended. This, of course, comes with extreme control issues that need to be engineered around. To begin, the engine needs to be throttled back as it expends fuel. As fuel is used, the weight of the rocket lowers. If the thrust isn't lowered, the rocket could exceed its max allowable dynamic pressure and disintegrate. An improperly designed fuel column could make matters even worse, as a simple circular internal cavity will result in an increase in thrust as the fuel is burned. However, many different thrust profiles can be achieved with different shapes. A pointed star cavity will start with higher thrust thanks to the increased surface area, but rapidly decreases in thrust as the points of the star burn down and the surface area decreases. This effect can be increased by increasing the number of points on the star, which is why the igniter had 40. Nearly every illustration online shows the Space Shuttle solid rocket boosters with a continuous cylinder. If this was the design of the fuel channel, it could have caused issues. The surface area of a circular internal cavity would have increased as fuel was burned, because the cavity's diameter and circumference would be increasing. This was not how the solid rocket boosters were designed. The upper section of the solid rocket booster had an 11-pointed star shape. This shape was created with this mandrel placed inside the upper section before the fuel mixture was poured in. This shape then transitioned into a circular section. However, it wasn't constant in diameter. The diameter increased towards the nozzle. This design provided elevated thrust at ignition when it was needed most, and then reduced gradually to lower the maximum dynamic pressure the Space Shuttle experienced, with the thrust decreasing by 33% 50 seconds into the flight. When filling the solid rocket booster segments with the propellant, they were filled in pairs, matching with its contemporary segment on the other booster. This allowed the two segments to be filled using the same batch of fuel mixture. So, if there were any inconsistencies in the mix, they would be at the very least consistent on the left and right side of the shuttle, ensuring differential thrust from the boosters would not drive it off course. However, all 5 of the nozzles were capable of thrust vectoring to control the Space Shuttle during ascent, and 80% of the steering power came from the solid rocket boosters, thanks to their power and increased distance from the central axis of the Space Shuttle. The Space Shuttle's aerodynamic flight surfaces played no part in control during ascent, but they did actuate to reduce aerodynamic stress and drag on ascent. 7 seconds after takeoff, with the Space Shuttle traveling around 140 km per hour, a roll program is initiated through asymmetric thrust vectoring of the nozzles of the solid rocket boosters with actuators mounted inside the aft skirt, here. There are 2 hydraulic actuators on each nozzle to allow it to move in both pitch and yaw. The Space Shuttle turns over 180 degrees and pitches 12 degrees off a straight up trajectory, placing the shuttle on a heading towards its assigned orbit, lowering the dynamic pressure on the shuttle's wings and providing the flight crew a view of the horizon out of their windows. Of course, this 180-degree rotation would not have been needed if the Space Shuttle was simply rotated on the launch pad. But the launch pad was designed for the Saturn V. The position of the service tower and all of the supporting infrastructure associated with it locked the Space Shuttle into this orientation, and it was simply easier to program a roll than to build a new launch pad. 45 seconds into the flight, something fascinating happens. The Space Shuttle exceeds the speed of sound, and the sound of those rocket engines can no longer reach the astronauts.
So you don't hear those rocket motors that much anymore behind you. But now you hear the air rushing down the side of the shuttle because you're in the thickest part of the atmosphere, and it sounds like a train howling through a tunnel when that air is going across the rough blankets and tiles on the outside of the shuttle.
And as the Space Shuttle races higher and higher into the atmosphere and the air gets progressively thinner, even this sound begins to dwindle away.
For the last 15-20 seconds of first stage, it's just a quiet, very rough ride because you're still on the solid rocket boosters.
And it will get even quieter as the solid rocket boosters reach the end of their fuel supply 2 minutes into the flight. Lowering chamber pressures triggers sensors to begin the separation process. However, if these fail, a backup system based simply on time elapsed takes over. Once triggered, the thrust vectoring system is commanded to return the nozzles to the neutral position, and the orbiter is commanded to maintain its attitude for 4 seconds. The SRBs are attached to the external tank at 4 points, through 3 struts on the lower section of the rocket and an additional upper connection, each held in place by frangible connections that are severed on command. At the same time, 8 separation motors, 4 on the top of the solid rocket booster and 4 on the bottom, fire. These were also solid motors and provided 96,000 newtons of thrust, ensuring the SRBs safely detached from the Space Shuttle as it continued its flight to orbit. This solid rocket booster separation process was the thing that caught Bruce off guard most on his first flight.
Picture this, you're sitting on top of the explosive bolts that are holding the boosters to the tank. So when those explosive bolts let go, it's a large bang, and then the booster separation motors, which are little rocket motors that fly the boosters away from the shuttle so it doesn't recontact it, those exhausts are aimed right at your windshield. So it's staging, instead of there being this little pop and off you go in second stage, it's this big bang, and then you're in this fireball where the exhaust from the booster sep motors are over the windshield, and it's like, geez, did we just blow up? And then very quickly, you get through that, and you can see the nice dark purpleness of space ahead of you. So that's really the only surprise going uphill that I had on my first flight.
At this point, the SRBs are continuing to climb in altitude, just slower than the space shuttle. Upon reaching their apogee, roughly a minute later, they will begin their journey back down to Earth, eventually releasing a series of parachutes from its nose cone to slow its descent and land in the ocean to be recovered and reused. Meanwhile, the orbiter is continuing its journey in its second stage of flight.
Second stage is smooth. Matter of fact, most astronauts will call it electric drive. But now's when the G's start to build up, and you're getting pushed further and further back in your seat. And then we throttle the engines back when we reach 3 Gs, because it is a winged vehicle, so there's a lot of aerodynamics going on there. And for the structural integrity, we go ahead and throttle back to 3 Gs because the wings could come off if you accelerated a whole lot more than that, and that would make for a bad day.
Under the power of the 3 main engines, fed with the liquid hydrogen and liquid oxygen from the external tank, the shuttle continues its way to orbit. This external tank is a bit of an anomaly. The space shuttle was intended to be fully reusable when it was first conceived, with the fuel and oxidizer tanks incorporated into the orbiter itself. In fact, the space shuttle was envisioned in many forms. Ultimately, funding challenges forced the space shuttle's ambitious designs to be simplified, and the Air Force was approached to bolster funds, influencing the design to stray even further from the original vision, primarily in an increased cargo bay capacity and increased glide range. The external tank was, however, the largest compromise of design. Gone was the idea of a manned external tank that would glide back to land. What would have saved money in the long run simply would have been too expensive to develop, relying instead on an expendable external tank, a massive non-reusable structure that would disintegrate during re-entry. The external tank was heavy. It wasn't simply 2 pressurized tanks. It was a structurally integral component, responsible for transmitting enormous loads. It was the centerpiece of the space shuttle system, the structural backbone, connecting to both the solid rocket boosters and the orbiter. In order to do this, the external tank had to be strong. It was 47 meters long and weighed 33.5 metric tons, empty. Its aluminium skin is reinforced with strengthening rings and stringers. This was essentially a massive thermos flask with a spaced double skin to insulate the cryogenic fuel inside. Finally, the entire structure was covered in a layer of orange insulation foam, which alone weighed 2.2 tons. The first 2 space shuttle missions featured a white external tank, coated in a fire-retardant latex, which was removed to save a quarter ton of weight. The liquid oxygen tank was located on top of the external tank. It's much smaller than the liquid hydrogen tank, thanks to oxygen's much higher density, and this is part of why the liquid oxygen tank was placed on top of the external tank, as it pushes the rocket's center of gravity higher, an important aspect of stability in flight. If a rocket is traveling straight up, drag and lift acts through the center of pressure. The location of the center of pressure is determined by the location of the aerodynamic surfaces and engines, but the rocket rotates around the center of gravity, which is determined by the placement of mass. Because of this, it makes sense to place weight higher on the rocket, as it moves the center of gravity above the center of pressure. Imagine a rocket flying with its orientation aligned with its direction of flight. When a gust of wind knocks it off balance, it introduces an angle of attack, which creates lift acting through the center of pressure, and the rocket rotates around the center of gravity, returning the rocket to its original position. If the center of gravity was below the center of pressure, the opposite would happen, and the rocket would be unstable. So, the dense liquid oxidizer was placed on top of the external tank. This came with the added benefit of allowing the intertank to be placed higher on the external tank, as the hydrogen tank is much larger. The intertank is a load-bearing structure between the 2 tanks. There is even a massive beam hidden within this intertank, resisting enormous compressive loads as the solid rocket motors attempt to push inwards. The lower support holding the solid rocket boosters takes all of the shear stress created by the upwards thrust of the booster, and so the upper support acts primarily in compression. The forward attachment point to the orbiter is also located on the lower portion of the intertank. Of course, all of this liquid oxidizer and fuel needed to get to the main shuttle engines on the orbiter. The liquid oxygen exits the tank here. This pipe is massive, 46 centimeters wide, big enough to crawl through. When the liquid oxygen begins to flow, it acts much like water, and with this rate of flow, a massive whirlpool could form. With the weight of all this fluid swirling and sloshing inside the tank, this could cause massive instability issues, or it could even expose the outlet and allow bubbles to enter the engine. So, anti-vortex and anti-sloshing baffles are placed on the bottom of this tank where the oxidizer exits. Liquid oxygen travels down this pipe into the interstage, where it exits and runs along the length of the outside of the liquid hydrogen tank until it meets the primary orbiter connection point. This connection point connects physically to the orbiter, but is also the primary connection for the liquid oxygen and liquid hydrogen. To the left and right of this truss connection are two umbilical plates, which mate directly to corresponding plates on the underside of the orbiter. The left plate provided a connection for liquid hydrogen, and the right plate provided a connection for liquid oxygen. Each also had gaseous lines that brought back gaseous hydrogen and oxygen from the main engine to their respective tanks. This was vital in order to maintain ullage pressure. Ullage is the volume of gas above a liquid storage tank, like the cryogenic liquid oxidizer and hydrogen tanks. The pressure of this volume has to be maintained as the liquid lowers. If the pressure is allowed to lower, the structural integrity of the tanks could be compromised. The gaseous hydrogen used to pressurize the tank was tapped off from the hydrogen fuel line after it went through the regenerative cooling loops of the nozzle here at the outlet of the turbine exhaust manifold of the low-pressure fuel pump. Liquid oxygen did not pass through this regenerative cooling system and thus needs to be converted into a gas to pressurize the tanks. It instead was tapped off here at the outlet of the main oxygen turbopump after passing through a heat exchanger around the turbine of this pump. Finally, there were electrical connections on each plate too, made up of smaller electrical wires that provided power to the external tank and solid rocket boosters, while also carrying vital telemetry data from each of the orbiter's computers. Finally, there was also the liquid hydrogen recirculation connection, which was only used during the liquid hydrogen engine cooldown sequence before launch, where the cryogenic fluid is circulated through the feed lines, valves, and turbopumps to bring them down to temperature. If this didn't occur, bubbles could form. The time for main engine cutoff is quickly approaching. The process will be triggered by a predetermined velocity target, around 28,000 kilometers per hour. However, it can be triggered by fuel and oxidizer sensors detecting a low fluid level. There are 8 propellant depletion sensors. The 4 fuel depletion sensors are located on the bottom of the liquid hydrogen tank. However, the liquid oxygen sensors were located downstream of the feed line, inside the orbiter. There was also an extra 500 kilograms of liquid hydrogen loaded over the required 6:1 oxidizer fuel mixture ratio. Together, these ensured that in the event the main engine was cut off as a result of propellant depletion, that main engine cutoff occurred in a fuel-rich scenario, as oxidizer-rich engine shutdowns severely erode and damage the reusable engines. The time has now come for the main engines to shut down and for the external tank to separate. Frangible nuts once again explode to separate the two structures. The external tank begins to float away, leaving the umbilical plates underneath the shuttle exposed, and fixing that is the next challenge.
You've got to close those doors. That's one of the first things you do, and that's very, very critical, because if you don't close those doors, you can't re-enter, because you'll burn up during re-entry. And so that's one of the things that we've talked about, we've learned about, but nobody has ever really thought about, or no one has ever really come up with an easy solution. If you had to do an EVA to close those doors, how you'd ever do it. You'd have to do a spacewalk back to the back here somehow, and maybe hold on to there's just no easy way to get underneath there to close those. But we talk about it, we come up with some ideas, but never had to be done, and there was never a procedure set to do it.
Thankfully, these doors successfully closed on every single space shuttle mission. The external tank is now on its way back to Earth's atmosphere, helped along by a vent opening in the oxygen tank that causes the tank to tumble away from the orbiter. With the thrust of the main engines gone, the astronauts have instantly become weightless. A serene moment that filled Bruce with so much joy that he forgot his first job as a rookie astronaut.
Now, we always took a nice close-up picture of the external tank right after MECO, because if you'll remember, the external tank was the only part of the space shuttle that wasn't reused. You know, the boosters would fly back or splash down in the ocean, we'd tow them back in, refurbish them, the shuttle would come back, but the external tank, as soon as we got off the tank, it would start tumbling back to Earth and break up and burn up, re-entering the atmosphere and just splash down in little pieces. So we always wanted to take a nice big close-up picture of the tank right after we got off it to see if there was any abnormality with it that might be generic that we'd need to fix before the next shuttle took off. So my very first job as a rookie was to, as soon as we got to MECO, instantaneously zero-G, was to get unstrapped out of my seat, float down to a locker by me, get the proper camera out, float up to the overhead window while Dick Richards, the commander on my first flight, was pitching Discovery over on its back so that we could take a picture of this tank as it's following away back to Earth. Well, I floated up to the overhead window and I'm looking outside and Dick says, "Hey, Bruce, you should be seeing it." And I said, "Yeah, Dick, I do. It's awesome. It's beautiful." He said, "Well, why aren't you taking any pictures?" I said, "Pictures of what?" "Oh, the tank." I was so blown away by seeing Earth for the first time from the space shuttle that I choked on my first job. And you know, I was supposed to have this great big picture of the tank. Well, by the time I took a picture of the tank, it was like falling away from us, but it was just beautiful. It was just seeing the Earth for the first time from space is, you know, probably my most memorable experience.
As Melnick got briefly distracted by seeing the beauty of space for the first time, the commander of the space shuttle was pitching the shuttle onto its back using its maneuvering system. Scattered all over the orbiter are smaller rocket nozzles, part of the reaction control system. This removable module in the nose of the aircraft was the forward reaction control system. Inside, there are two spherical tanks, an oxidizer tank filled with nitrogen tetroxide, and a fuel tank filled with monometal hydrazine. This fuel oxidizer combination is unique. It doesn't need an ignition source. It's hypergolic, meaning they spontaneously ignite upon contact with each other. But both substances were extremely toxic, producing ominous orange clouds of toxic gas. Breathing this in would cause your lungs to rapidly fill with fluid, and once in your bloodstream, it interferes with the blood's ability to carry oxygen. Anyone working with these propellants had to wear pressurized breathing suits to prevent any chance of contact. The astronauts also had exclusion zones around these nozzles on spacewalks to prevent any danger of the chemicals coming back aboard. It's an undesirable fuel to work with in many ways, but its advantages were why it was used. These hypergolic fuels were extremely reliable. Igniting on contact with each other removed any need for complicated ignition systems that could fail. They could be stored for longer periods than cryogenic fuels that would have to be continually vented as temperatures rose, which makes cryogenic fuels unsuitable for longer missions like the Space Shuttle. With the longest Space Shuttle mission lasting 18 days, this was critical. The propellants could also be quickly mixed in precise volumes to provide precise and instantaneous thrust control. This was important when maneuvering in close proximity to another spacecraft. The propellants are fed into the combustion chamber through pressurization of the tanks with high-pressure helium, held in spherical Kevlar composite tanks with titanium inner liners. An extremely lightweight tank, just 10 kilograms in weight, but nearly a half meter in diameter. Spherical tanks are the most weight-efficient form of pressure vessel, with the highest volume-to-weight ratio. Ideally, all rockets could use spherical tanks, but ultimately, diameters increase too much as volume requirements rise, and it's preferable to minimize the cross-sectional area of the rocket to reduce drag. There is no turbopump needed here. The back pressure from the high-pressure helium provides enough flow rate for the purposes of these low-power rocket motors. In the Forward Reaction Control System pod, there are 12 main thrusters, and there are 12 in each of the left and right rear pods too, for a total of 38 main thrusters, each capable of providing 3,870 newtons of thrust with a specific impulse of 289 seconds. Sometimes even finer control was needed for delicate docking procedures. And for this, the orbiter had 6 smaller vernier thrusters, capable of producing as little as 111 newtons, the same amount of force you would need to lift an 11-kilogram weight here on Earth. With a total of 44 reaction control thrusters scattered around the orbiter, the astronauts needed a way to control them. The controls were located at the commander's seat on the left side of the cockpit and here on the left side of the aft flight deck. The rear position was added to allow the commander to look out this rear window while maneuvering for rendezvous with other spacecraft or releasing payloads. Each station had a square-knobbed controller used for translational movements, in and out, side to side, and up and down, and a more traditional flight stick, which was used to control attitude, pitch, roll, and yaw. There was also a flight computer where desired altitude and velocity changes could be entered with a keypad. Of course, this was all fly-by-wire. The commander's inputs were all fed into a computer which interpreted the commands and decided the best course of action. There was only one notable exception for this fly-by-wire system.
I mean, there is nothing mechanically linked to any of the control surfaces or anything. Everything goes through the computer. Everything you touch goes through the computer, and the computer generates everything. We're concerned about things called single event upset. You've probably heard of those before, where a cosmic ray comes in and upsets the computers, and you can recover from anything. But because there was no way to raise the landing gear, we were concerned a single event upset, if there was an automatic computer's way to lower the wheels, that you could get your wheels lowered on orbit and not be able to come home. So we always made that mechanical, and so once we got down to under 300 feet, 200 feet, that was the pilot's main job, was to lower the wheels manually.
Putting them back in place required ground crew to push them back in. So, because ionizing radiation in space could potentially trigger the computers to lower the landing gear, and with no way of raising them back up, they were lowered manually. The landing gears were held in place by a hooked lock that was released after the pilot flipped the protective covers on these 2 buttons, an arming button and a button labeled DN for down. When this happened, a hydraulic actuator released the hook, holding the landing gears in place and allowed them to lower. The first day of the mission is now starting. The astronauts begin their tasks. The pilot and commander, seated in the left and right seats in front of the instrument panel, are busy working towards the first rendezvous with Intelsat. Through the forward windows, the astronauts can glimpse a distant bright dot, the satellite they are maneuvering towards. These weren't the only windows on board. There were additional overhead windows, along with rear windows looking into the payload bay, which for now remains closed. These windows were key to the reusability of the shuttle. The windows had to be durable enough to survive space debris impacts and capable of resisting the temperatures of re-entry. The Space Shuttle's window structure had multiple layers of glass, each tailored to withstand different conditions. The pressure pane was engineered to endure the cabin pressure in space. It was made from 15.7mm thick alumosilicate glass that was tempered to be mechanically strong. On the outer edge of this pane, a red film was added to reflect back the heat into the vehicle so it wasn't lost to space, while still letting visible light through. The outermost pane, or the thermal pane, was also 15.7mm thick and capable of resisting temperatures of up to 482 degrees Celsius. There was also a large space between these 2 panes, which minimized heat transfer between the outer shell and the inner crew cabin. On one Discovery mission, one of these windows was struck by space debris, leaving a small crater in the window, but it did not break. If it had, the astronauts inside were in no danger, as there was also a center redundant pane, serving as a failsafe for both the thermal and pressure panes. It was 33mm thick and made out of fused silica glass, the same material that laboratory crucibles and beakers are made out of. The rear windows, looking into the payload bay, did not have the outer thermal pane, since they would not be exposed to the extreme superheated plasma during re-entry. There were no windows in the middeck below the crew deck. The middeck is where many of the science experiments in orbit were performed, and this is where the astronauts slept and ate. There were stations where the astronauts could strap themselves to the walls in the weightless environment, but not everyone chose to use them.
The commander and pilot generally slept up on the flight deck. They would just loosely strap themselves in their, commander and pilot seats, because that was a good way. And you want to be kind of strapped in. There were some astronauts like Story Musgrave that liked to free float around in space, but he would bump into people, and I heard that it was quite annoying sometimes. But the rest of us, you have a cloth sleeping bag that's made out of just light material like this, where you Velcro it to a bulkhead or the ceiling and you just zip yourself up in it.
The time has now come to open the payload doors. The doors needed to be opened shortly after reaching orbit, as one of the space shuttle's vital life support systems required them to be open, the temperature control system. 2 radiator panels are attached to each of the forward payload bay doors. Freon-filled tubes snake around these panels, where they radiate heat absorbed from a heat exchanger located inside the orbiter into space. The payload doors themselves are made from a graphite epoxy composite material, which reduced the weight of the doors by 408 kilograms over a comparable aluminium design. At the time, this was the largest aerospace composite structure ever made. Covering the payload bay, which was 18.3 meters long and 4.6 meters wide. The largest and heaviest payload it ever carried was on STS-93, with the Chandra X-ray Observatory coming in at 22.7 tons, maxing out the shuttle's capacity. This mission came worryingly close to disaster. During each refurbishment of the shuttle's main engines, they were inspected with ultrasound to find signs of damage. In some cases, damage may be detected in one of the liquid oxygen posts that delivered liquid oxygen to the combustion chamber, and instead of replacing the entire expensive and difficult to manufacture injection assembly, the post was simply deactivated with a gold pin that plugged the channel. During the pre-launch startup sequence of the main engines on STS-93, one of these gold pins was ejected out and struck the hydrogen coolant channels in the nozzle, resulting in a hydrogen leak that you can actually see here in images of the launch. The engine detected a decrease in combustion chamber pressure and opened the oxidizer valve to increase thrust. The engine had no way of knowing the issue was a hydrogen leak. It could only detect the drop in combustion chamber pressure and respond by making the combustion less fuel-rich, which increases thrust and temperature. This incident resulted in a maintenance policy switch that meant damaged oxygen posts had to be replaced and not simply plugged. Thankfully, the engine survived, and the mission was successfully completed, despite the main engines shutting down prematurely as a result of the oxygen depletion sensors being triggered. So, the orbiter was 4.6 meters per second off its target orbital velocity. Thankfully, the orbiter had an orbital maneuvering system that could bring it up to its desired velocity. These large rocket nozzles were not part of the reaction control system and were capable of providing 305 meters per second of additional velocity, powered by the same hypergolic fuel and oxidizer as the RCS system, from tanks hidden within the OMS pods, capable of holding 4 tons of fuel and 6.7 tons of oxidizer. When performing large orbital changes like this, it was important for the space shuttle to know precisely where it was. And to do this, it could open these doors on the left side of the orbiter's nose, revealing the star tracker optics. These star trackers analyzed known positions of the stars in the sky to determine exactly where the orbiter was, allowing it to precisely navigate in orbit. Once the space shuttle has arrived at its target orbit, the real work can begin. On Bruce's mission, STS-49, the first task was to rendezvous with that stranded communications satellite, carefully maneuvering the orbiter closer to the satellite as the satellite's operators attempted to stabilize its spin. As they approached, 2 astronauts, Pierre II and Richard Heeb, donned their EVA suits in the middeck and prepared to enter the airlock. The airlock for this mission was located inside the crew cabin of the middeck, but it could be configured to be outside in the payload area. During the construction of the International Space Station, a special docking system was also installed, which was required to allow the space shuttle to dock to both Russian and American spacecraft. It was called the Androgynous Peripheral Attach System. The androgynous name comes from the fact that both the target and the receiving end look identical, with no male or female parts, with the goal of this being a universal docking system, allowing any two spacecraft to dock together, as Goddard intended. Each side had a ring with 3 petals equally distributed. One side extended its mating ring for a soft capture, where the 3 petals of each side come together and connect with these latches. At this point, the soft capture ring is retracted and 12 latches engage to form an airtight connection between the 2 spacecraft. This system was used extensively during the construction of the International Space Station, which the Space Shuttle had an instrumental role in transporting and assembling in space, including the very first modules to be connected in 1998 on STS-88, when the orbiter docked with the Russian Zarya module using this docking ring and proceeded to connect the Unity module. On STS-49, Bruce's mission, the stranded satellite was never intended to be docked with and had no docking points, and thus, to capture the stranded satellite, the astronauts needed to perform an EVA and manually grab the satellite using a capture bar specifically designed for this mission, but not everything went to plan.
So we made several attempts to grab this satellite with the capture bar, but every time Pierre touched the bottom of the satellite with the capture bar, it bounced off out of control. Fortunately, the engineers that owned Intelsat, they could send commands back up to it, restabilize it so we could maneuver back closer to it and try again. So we tried 3 or 4 times the first day to grab it, every time it bounced off. Second day we tried again, every time it bounced off. So at that point, we were kind of at a loss. We didn't know what we were going to do. And of course, all this time, I'm operating the arm. I'm chasing the satellite with Pierre on the end of it. And so it was a very demanding part of the flight. So after 2 days of trying, the ground said, okay, we're gonna take the 3rd day off. And then we'll go back out and try on the 4th day to do it again. Well, of course, we felt like the mission was lost. So, you know, the ground told us, go ahead, get a good night's sleep, we'll call you in the morning. So we got to thinking, and matter of fact, I saw that I could hear that Dan and Chili were talking up on the flight deck. We were supposed to be asleep. So I floated up to the flight deck with them, and they were talking about how Endeavour was so maneuverable and was so efficient on its fuel burn that they thought we could get close enough to the satellite to where Rick and Pierre could just grab it with their gloved hands. And we saw it at one point when Pierre got the capture bar, one side of the capture bar fired, and it almost immediately stopped the rotation. So we knew that it was going to be easy to stop the rotation if Rick and Pierre could just grab the bottom of this satellite. The problem is now what do? If you do grab the satellite, you've got 2 guys out there holding a 9,000-pound satellite with no way to get it back on the rocket motor that we took up to strap to it to send it back up to the proper orbit. Well, I scratched my head while I was up there, and I knew that because after we finished this satellite business, 2 other astronauts, Tom Akers and Kathy Thornton, they were going to go out and do some practice of assembly of the space station. You know, we hadn't built the space station at that point, and they were going to be out trying to do some methods for that. Well, in order to accommodate all the different sized astronauts, the EVA suits, or the spacewalking suits, they're made out of different components, different length arms, different sized torsos, those sorts of things. And Rick Heeb is this big, Kathy Thornton was this tall, and then Tom and Pierre are about my size. So in order to accommodate 4 astronauts on 2 different spacewalks of those different sizes, we, for the first time ever, had 3 full EVA suits, the components of 3 full EVA suits on board. So I got to thinking, I said, well, we have 3 suits on board, why don't we send 3 spacewalkers out? You know, we can have 2 people grab it and then 1 person put the capture bar on, because the capture bar had to be attached to the satellite because that was what was going to attach it to the rocket motor that we brought up.
However, this plan had one problem. The airlock was only designed for 2 people. The airlock consisted of 2 airtight doors. Once inside with the door sealed, the astronauts could depressurize the inside by venting the air to space. This could only be done from inside the hatch, but repressurization could be done from outside and inside for obvious safety reasons. This process took about 30 minutes, and while it happened, the astronauts were connected to life support umbilicals so that they didn't have to waste their internal supplies during the wait. This was the first problem. There were only 2 life support umbilicals available. It was also going to be a tight squeeze for 3 astronauts with full EVA gear on, as the cylindrical airlock inside the mid-deck was just 160 centimeters in diameter and 210 centimeters high. The 3rd astronaut was going to need to make some sacrifices.
So unlike normally where you just have 2 astronauts, you put them in the airlock, you close the door, with Tom, he had to go on all of his internal controls, and we float him in the airlock upside down. So now you've got Rick and Pierre right side up and Tom Akers head down in the airlock, and he's on his internal systems now where Rick and Pierre are still attached to the umbilicals inside. Close the airlock, evacuate it, and then all 3 of them floated out.
And here, the 3 astronauts got to work, with Bruce on the remote manipulator arm controls inside the orbiter, and he was chosen for a very specific reason. He was a Coast Guard helicopter pilot.
And the reason, Dan wanted to have a Coast Guard helicopter pilot on the arm. And the reason for that is that operating the arm, the controls that you use are vaguely similar to operating a helicopter, because in a helicopter, you have to fly with both hands and both feet. Well, when you're operating the arm, you've got 2 controllers. You've got a rotational hand controller and a translational hand controller. So the translational hand controller, you move up, down, sideways, in and out. Rotational hand controller controls the attitude of the arm. So it's very much like flying a helicopter. And you can't be thinking about it. When you're in a very, tight situation, you've got to be the arm.
The Canadarm, named after its country of origin, was a multifunctional tool used for many tasks aboard the shuttle. A simple articulated arm may not seem overly impressive, but the unique physics of a weightless environment and the desire to minimize the launch weight of the space shuttle made for a very interesting engineering challenge. The entire 15-meter-long arm weighs just 430 kilograms, and despite being able to move 30 tons in orbit, it couldn't even hold up its own weight on Earth. The booms were made from low-weight epoxy graphite composite, with 6 joints, 2 joints at its shoulder for yaw and pitch, 1 elbow pitch joint, and 3 joints at the wrist for yaw, pitch, and roll, for a total of 6 degrees of freedom of movement, exactly like your own arm. However, your elbow is only capable of about 140 degrees of pitch before your bicep gets in the way. The Canadarm's elbow joint rotational axis is offset by 0.15 meters to allow up to 160 degrees of rotation. Because the arm is working in a weightless environment, the motors don't need to be able to apply that much torque. Each motor could only produce 0.7 Newton meters of torque. With no friction in space, a small force can move any mass. It just depends how long you want it to take. In the same way, ion thrusters with thrusts of just 25 millinewtons could theoretically get a spacecraft up to light speed if it had enough propellant. However, the dangers of inertia are still real. If a satellite was moving quickly relative to the arm, it could easily bend and break the arm. So, delicate movement is the name of the game, and the motor can work in reverse to assist each joint's brake system. The loaded arm speed had a maximum speed of just 6 centimeters per second. The arm had a unique end fixture designed to grapple onto attachment points on satellites. However, because the Intelsat was never intended to be rendezvoused with, it didn't have any grapple points installed. So, the capture bar had an attachment point for the second stage rocket and had a grapple point, allowing the Canadarm to grab hold of it once it was securely attached. The grapple point is a simple metallic pin with 3 lobes at its base. This is all the arm needed to firmly grab onto the Intelsat. The end effector of the Canadarm used a naturally self-centering wire grapple system to hold on to this pin. 3 wires, each anchored at 2 points. 1 point is stationary, while the secondary anchor point is attached to a rotating ring. Once Bruce had maneuvered the arm over the grapple rod using the camera feed, this rotating ring would turn and ensnare the pin, pulling it to the center. The pin is then pulled inwards until the 3 lobes at its base lock into corresponding cutouts on the outside of the grapple ring. a simple but effective mechanism. With the satellite now secure, the 3 astronauts could get to work attaching the new second stage to the capture bar, which they did successfully, allowing the Intelsat to raise itself to geostationary orbit, where it operated for 21 years. STS-49 had another mission to complete, a test run of space shuttle building techniques, but with their time in orbit running out, that mission lost a day. Life support systems on board were supplied with enough gases for the planned duration of the mission. Spherical tanks in the mid-fuselage contained high-pressure oxygen and nitrogen, with 3 nitrogen tanks and 1 oxygen, used to create a breathable atmosphere of 80% nitrogen and 20% oxygen. Of course, carbon dioxide needed to be scrubbed from the air, and this was done by passing the cabin air through lithium hydroxide canisters located underneath the middeck. These solid canisters would react with the CO2 to remove it from the atmosphere and create water in the process. This was not a renewable solution, so every 12 hours the crew would access and replace these canisters through the hatch on the middeck bay. There were also oxygen and hydrogen tanks used for the space shuttle's power system, a fuel cell that reacted the hydrogen and oxygen to produce water and electricity. These powered everything on board and produced water in the process, but this water carried some extra hydrogen gas, so before the water could be used, it had to go through a process of degassing, which separates the hydrogen and dumps it overboard. It was now time to prepare for re-entry, and the first step was closing those payload doors. But on STS-49, another problem was encountered. The payload doors would not latch due to thermal warping of the doors, requiring some creative problem solving.
There's always 2 astronauts trained to do EVAs, and I was trained to do an EVA on my first flight, and that's for a contingency if, for example, the payload bay doors wouldn't close or latch all the way when you're on orbit. We have special tools where we could winch them closed and latch them all together. And matter of fact, on STS-49, after we had trouble getting the satellite to launch because of a different switch configuration, we got up there and the payload bay doors wouldn't close all the way. And so we thought, oh man, do we need to go back out and do that? So your first attempt to fix something like that is the thermal loads on the space shuttle. As you can imagine, you're 200 degrees in the sunny side and 200 degrees below zero on the dark side. So a lot of times you'll get a little bit of an oil canning effect or a little twisting of the fuselage just because of the thermal effects. And that's what we did. We went ahead in what we call the barbecue mode, and we went ahead and orbited the Earth in the barbecue mode to try to equalize the temperatures on the shuttle when we couldn't get the payload bay doors to close all the way. And
when you say barbecue mode, do you mean like a spit roast? It's like
yes,
rotating.
Yes, yeah. And I mean, it's not that fast, but you do that to where you try to equally heat while you're going, through the sun and through the dark. And I think it was just one orbit we had to do, and we tried to close the doors again, and they latched.
With the doors successfully closed, the space shuttle could begin its preparations to re-enter the Earth's atmosphere. The re-entry procedure begins with a 2 to 4 minute burn of the orbital maneuvering engines, while the spacecraft is upside down and traveling backwards. With an orbital speed of around 7 kilometers per second, the OMS pods need to reduce the orbiter's speed by just 0.1 kilometers per second, 1.3% of its velocity, to lower its orbit enough to bring it into a collision course with the Earth's upper atmosphere. A precise maneuver, bleed too little speed, and the orbiter will overshoot its narrow window for success, skimming through the thin upper atmosphere and potentially bounce back into space. The orbiter has wings that generate lift, after all. Bleed too much speed, and the orbiter will descend through the atmosphere too fast, reaching the thick lower atmosphere before enough speed has been leached away, resulting in catastrophic overheating. This narrow entry window was called the entry flight corridor. Once the delicate retrofiring sequence has been completed, the next phase of re-entry begins. The reaction control system flips the shuttle around and places it into a 40-degree upwards pitch angle, ready to meet the Earth's atmosphere, entering the upper atmosphere at 30 times the speed of sound. The speed is so great it begins to rip air molecules apart, creating a glowing cloud of charged plasma around the lower surface of the orbiter, with peak temperatures reaching 1,650 degrees Celsius. Nothing like this had ever been attempted. A blunt body capsule, like every other re-entry capsule to date, designed purely for thermal protection, is an engineering challenge, but tack on the needs of an aircraft and the task gets vastly more difficult. Thankfully, NASA had a test run in 1959 with the X-15, the fastest plane in the history of humankind, and it advanced our understanding of hypersonic flight, providing many lessons that were incorporated into the space shuttle's design. However, the X-15 had one major advantage over the space shuttle. It didn't need to launch itself into orbit. It didn't even launch from the ground, instead launching from the belly of a B-52. This allowed the X-15 to use a state-of-the-art advanced heat-resistant aerospace metal, Inconel X, with a max operating temperature of 980 degrees Celsius. The space shuttle could not use this metal. Inconel X is too heavy, about 180% heavier than an equivalent aluminium airframe, a massive issue for an aircraft designed to be carried to orbit. The space shuttle's airframe, therefore, is not made from Inconel X. It is composed of lightweight aluminium, which has a max operating temperature of just 177 degrees, 5 times lower than Inconel X. The orbiter would experience temperatures 10 times greater than this for extended periods of its re-entry flight. To make matters worse, one of the principal lessons learned during the X-15 program was that the hot pink foam ablative coating sprayed onto the plane for the top speed flights was completely unusable for the space shuttle. An ablative coating is a sacrificial material designed to gradually burn and fall away from the aircraft, pulling the heat with it. However, the ablative coating of the X-15 had a nasty habit of burning away from the nose of the plane and begin attaching itself to the cockpit windows, rendering the pilots completely blind, which presented a bit of a problem. At one point, the engineers of the X-15 considered attaching small explosives to the window and intentionally exploding the outer pane of glass to remove the ablative stained window, leaving only the inner pane for landing. Thankfully, they came up with a much less risky solution of installing a mechanical eyelid to the left window that remained closed until the high-speed portion of the flight concluded, providing the pilot one clean window to land with. An extremely primitive solution that created stability issues, as the open eyelid acted like a canard, causing the plane to pitch up, roll right, and yaw right. Even more terrifying, this coating became explosive when mixed with the liquid oxygen, and could be triggered by even a slight impact. A massive safety concern for a plane that required a liquid oxygen oxidizer to operate. A danger that would be multiplied manifold with a vehicle filled with 500,000 liters of liquid oxygen. The ablative was also not reusable, which would drastically increase the cost of refurbishing the shuttle between flights. The space shuttle would need to be better. As the space shuttle descended through the atmosphere, its nose and wings bore the brunt of the re-entry heat. The high-pressure shockwaves forming around them have created a layer of superheated plasma. If this heat managed to find its way into the delicate aluminium framework inside the orbiter, it would be game over. This is exactly what happened to the Columbia shuttle as a result of damage to the leading edge of these wings. The first step in protecting the orbiter's surface was to keep this superheated plasma as far away from the surface as possible. The nose, wings, and belly of the orbiter was carefully crafted to ensure shockwaves were kept at bay. We can see how using Schlerin imaging. A pointed missile-like vehicle pierces through the air with efficiency, and in doing so creates a shockwave, attached to its nose with an angle determined by its Mach number. This shockwave is simply a region of incredibly high pressure, and with that pressure comes incredibly high temperatures. This can have disastrous effects, as DARPA experienced twice in 2010 and 2011 when testing their sharp-nosed hypersonic re-entry vehicle, the HTV-2. Within 9 minutes of re-entering Earth's atmosphere, both vehicles disintegrated as a result of the 1,900-degree heat penetrating their metallic skin. The HTV-2 completed its mission of collecting hypersonic flight data, but the space shuttle needed to not only survive this mode of flight, but to do it repeatedly with minimal refurbishment. A good portion of this heat could be kept away from the aircraft's skin with blunt-bodied design, which creates a rounded bow shockwave with a layer of insulating lower pressure air between the vehicle and the shockwave, reducing heat transfer. For this reason, the space shuttle's surface is carefully molded to take advantage of this phenomenon. The rounded nose cross-section gradually transitions to a blunted triangle. This shape minimized the heat reaching the less protected sidewall of the shuttle, which used lower temperature insulation. We are now 7 minutes into the re-entry procedure, having descended 50 kilometers in altitude, but only shedding 0.5 kilometers per second of our velocity. We've entered the period of maximum re-entry heat, a confluence of speed and atmospheric density. The layer of superheated plasma surrounding the shuttle is blocking communication to the computers and astronauts inside, a result of free electrons in the plasma interfering with electromagnetic communication techniques, a problem that would last for the next 12 minutes. For now, the shuttle is operating on its own telemetry data, ensuring that 40-degree angle of attack is maintained. Managing that angle with a velocity of 6.5 kilometers per second was no easy task. A massive control surface was needed. The elevons on the outer wing would not suffice. This is where the rear body flap came into play. It was a massive control surface underneath the shuttle's main engines, covered in high-temperature insulation. The body flap doubled as a heat shield for the shuttle's main engines. With no cooling liquid hydrogen running through the nozzles, the flap was needed to shield the engines from the heat of re-entry. On the Space Shuttle's third flight, the Kuiper Airborne Observatory flew underneath the orbiter as it re-entered and captured an infrared image of its searing hot belly, an experimental program to validate NASA's newly developed computational calculations and experimental testing. This is what it saw. The nose and leading edges are a scorching 1,500 degrees Celsius, far beyond what the aluminium airframe underneath is capable of enduring. These leading edges, experiencing the hottest temperatures, needed the most heat-resistant material on the entire shuttle, a reinforced carbon-carbon composite, one of the amazing materials created in the years between the development of the X-15 and the Space Shuttle. A carbon composite manufactured with a special post-processing step. It was initially manufactured like any other carbon fiber part, a carbon fiber weave molded into shape and bound together with a resin. However, the heat of re-entry would set the hydrocarbon resin on fire without special treatment. The post-processing step would solve this problem. The carbon composite is placed in a vacuum chamber and heated, causing the hydrocarbon resin to decompose, releasing the hydrogens, leaving layers of pure carbon behind, graphite. Carbon fibers bound together by a maze of graphite, strong and capable of withstanding 1,510 degrees Celsius. They face head-on into the inferno of hypersonic flight. The leading edge of the orbiter's wings is composed of 22 of these carbon-carbon panels, with sealing strips covering expansion gaps between each panel, an essential solution to a lesson hard won during the development of the X-15. To investigate the heat of hypersonic flight, the X-15 was painted with a special kind of paint that reacted to heat. And after one flight, the X-15 returned with strange, wedge-shaped patterns emanating from the leading-edge expansion joints, small gaps in the leading edge to allow the Inconel skin to bend and contort with the wing without buckling. This localized heating was happening as a result of turbulent flow, increasing the rate of heat transfer to the metallic skin of the aircraft. To fix this, small floating strips of Inconel were placed over the expansion gaps. These strips of reinforced carbon-carbon serve the very same purpose. However, there is one more problem. Carbon is a thermally conductive material, not ideal for a heat shield. The Space Shuttle has been traveling through the atmosphere for 15 minutes, but is still traveling at 6 kilometers per second, and contact has not been re-established through the cloud of plasma surrounding the aircraft. This is a sustained heat, and with carbon being conductive, this heat could make its way to the aluminium airframe over this period of time. If these carbon-carbon shields were attached directly to the airframe, the heat would come in direct contact with the metal, raising it above its max operating temperature. To prevent this, the panels were fitted with Inconel attachment points that attach to the aluminium airframe with Inconel bolts. Inconel, being mostly made of steel, is a poor conductor of heat and could handle the heat the carbon parts transferred to it, without easily transferring that heat to the aluminium. This wasn't enough to protect the interior of the shuttle, however. A layer of insulating tiles were placed underneath the carbon-carbon shield too, the same insulation that was used on the underside of the entire orbiter. The Space Shuttle Columbia had 32,000 of these tiles in two flavors, low temperature and high temperature, white and black. But both of these tiles were made from the same base material, silica fibers, just a few millimeters thick, which, by volume, made up just 10% of the tile. The remaining 90% was nothing but air, an excellent insulating material, a thick and light tile, composed of a material with a high operating temperature. The coating is where the tiles differ. The black tiles installed on the lower portion of the shuttle were covered in a black borosilicate and tetraboron silicide glass coating. This black coating helps dissipate heat before it can conduct to the vulnerable inner structure. Black for the same reason the SR-71 is black, Kirchhoff's rule of radiation. This rule tells us a good infrared heat absorber, basically anything black, is also an equally effective heat emitter, with the heat gained from hypersonic flight vastly higher than the heat gained from solar radiation. It's preferable to prioritize outward heat radiation than minimizing heat gained from solar radiation. So why isn't the entire Space Shuttle black like the SR-71? The Space Shuttle has one important difference with the SR-71. It exited Earth's atmosphere. Once outside the Earth's atmosphere, the intensity of solar radiation increases drastically. With the longest orbiter mission at 17 days, this heat had plenty of time to conduct through to the people inside. The orbiter did have huge radiator panels to reject heat to space, but to minimize their size, we want to reflect as much of that heat back into space, and for that reason, they are white. These tiles were coated with a similar glass coating, but with an aluminium oxide additive to provide the white coloring. The coatings also help to waterproof and strengthen these porous tiles. The tiles were assembled like a giant, precisely engineered puzzle with 32,000 pieces. Each tile assigned a serial number that corresponded to their location, shape, and thickness. The tiles were created by mixing cotton-like silica fibers with water. This mixture was then cast into large blocks and were then dried in a microwave oven. Once dried, they could be cut into smaller sheets. The tiles varied from 25mm to 127mm thick, with the 127mm tiles insulating up to 1280 degrees Celsius. These sheets were then cut into their precise shapes according to their assigned serial numbers, using a computer-controlled milling machine. We are now coming through to the end of the communication blackout, and enough of the heat of re-entry has reached the aluminium airframe to cause it to expand. A major problem, as these tiles are not flexible in the slightest and are quite fragile. The expanding airframe could easily break the tiles and open up a path for the superheated gas to penetrate inside. The engineers needed a way to allow the structure to move beneath the tiles without causing the tiles to pop off. To do this, the tiles were first glued in groups to a layer of flexible Nomex felt. This Nomex fabric allowed the structure beneath to flex, expanding the lower side of the felt without transferring that strain to the upper layer attached to the tiles. These tiles and felt were then attached to the shuttle using the same adhesive, a commercially available high-temperature RTV adhesive, a bright red silicone-based adhesive. To prevent collisions between tiles, gaps between 0.46mm and 1.9mm were included. Thankfully, the issue of turbulent flow created by expansion gaps primarily affected the leading edges of the wing, so these gaps were not covered on the exterior of the shuttle. In areas exposed to lesser temperatures, flexible heat shields were used, constructed from high-temperature silica and Nomex fibers to create a flexible fabric which were sewn together with the same fibers, giving a quilted blanket appearance, with the Nomex fabric capable of resisting temperatures up to 370 degrees, and the silica fabric capable of tolerating temperatures up to 650 degrees. These were lighter and easier to replace than the tiles, being bonded directly to the structure again with that bright red silicone RTV adhesive. We are now out of the communication blackout and approaching 4 km per second or Mach 12 in velocity, and are about 45 km in altitude, about 4 times the cruising altitude of an airliner. The orbiter has maintained that 40-degree angle of attack this entire time. Being forced to hold an angle of attack this large comes with some control problems. The orbiter needs to land precisely on a landing strip from orbit. Managing its trajectory while being stuck with its nose up would be difficult. especially for a glider with no way to add energy once it's been bled away by drag. If the space shuttle wanted to lower its lift and lower its altitude faster, it could not lower its angle of attack. So the shuttle needed a special way to adjust its trajectory to adjust its landing area. Instead, the orbiter decreased its lift by banking. This split the lift into vertical and horizontal components, reducing the lift keeping the shuttle in the air and trading it for lift that moved it sideways. This is what a typical re-entry flight profile looked like. This line is the angle of attack, keeping steady until Mach 12, and then gradually reducing as it descends through the thick lower atmosphere. And this is the bank angle. As the orbiter crashes down from orbit, it banks wildly from side to side. The astronauts inside, who are already pointed 40 degrees up, are now tilted on their sides up to 70 degrees. The orbiter is essentially doing the fastest drift in history. There are some quirks to flying this high in the atmosphere at hypersonic speeds. The bank angle controls actually work in reverse to normal. If we deflect the right elevon down, it should increase lift on the right wing and cause that wing to rise, banking the aircraft anti-clockwise. But it doesn't. When the elevon is deflected downwards into the already compressed hypersonic air, it causes drag to rise on the outer wing. This causes the orbiter to turn its nose in that direction. As the nose turns in the direction of the deflected elevon, it shields that wing and causes a decrease in lift, causing the shuttle to bank in that direction. So, where a downwards deflecting elevon would typically cause an increase in lift on the wing, here, through a series of events, it causes a decrease in lift, working in reverse. Of course, this bank angle causes the orbiter to drift off target for its landing, and to correct, it needs to bank the other way. The orbiter has now slowed down to Mach 3, and at this point, the flight crew deploy air data sensors to aid in the final approach. Two probes rotate from underneath the heat shield on either side of the nose, providing airspeed, angle of attack, and temperature data to the flight computer. At this point, the orbiter is flying like a plane. But it's not a plane, it's a glider, and the flight crew needed to carefully manage the remaining energy to land safely. Especially as the orbiter was not built like a traditional glider. Balancing the need to survive re-entry while maximizing lift efficiency was a unique engineering challenge, made more difficult by Air Force funding, causing the design to skew closer to a plane than a re-entry vehicle. Early concepts of the shuttle drew inspiration from the X-15 with much smaller wings, more than enough to land the original smaller orbiter on a runway. The Air Force wanted a larger payload capacity, and they had one more specific requirement that required bigger wings. They wanted the space shuttle to be able to take off from Cape Canaveral, complete its mission, and land back at Cape Canaveral after a single orbit, essentially treating the space shuttle like a military operation to avoid Soviet attention, fast and elusive. This came with some issues. A single orbit took 90 minutes, in which time the Earth rotated below the shuttle's orbit by 2,000 kilometers. So, to return to its launch location, the orbiter would need to be capable of flying laterally by at least 2,000 kilometers. This is called cross range. The original X-15 inspired design was capable of just 370 kilometers of cross range. North American Rockwell proposed this huge blended body delta wing concept in 1970, which would have given the orbiter 2,800 kilometers of cross range. The fully reusable concept, with its crude booster rocket and internal fuel tanks, were not to be, but the large delta wings endured. These delta wings provided enough lift in both hypersonic, supersonic, and subsonic flight regimes to provide the cross range needed to reach the original launch site after a single orbit. Despite that, the space shuttle was an unwieldy aircraft, and with no powered flight, the commander had one shot to land it safely. So, they had to go through intensive training. In 1973, NASA created 4 training aircraft by modifying 4 Gulfstream jets to fly like the space shuttle. In order to mimic the immense drag the blunt body design of the space shuttle would create, the Gulfstreams flew with their landing gear down and their engines working in reverse, and flew with their flaps deflected upwards to decrease lift. With flight characteristics like this, the space shuttle needed to carefully manage its energy. Losing too much altitude far from the runway would be far from ideal. The pilot's aim, guided by beacons and ground control, for a tangential entry into a circular approach path, 5,800 meters in diameter, just off the runway. The moment they intercept the circle, the Space Shuttle commences a deep spiraling turn. At this point, the Space Shuttle is still traveling at about 0.8 Mach, still very fast, and it's at this point the wings are stressed the most, hitting a higher max dynamic pressure than at any point during the re-entry process, due to the higher air pressure at this altitude. And the shuttle's descent rate increases, now losing altitude rapidly with the knowledge the runway is within a safe gliding distance, descending to about 3,000 meters in altitude and slowing to about 0.5 Mach. At this point, the shuttle enters a straight 20-degree down glide approach path, much steeper than any airliner approach path, bleeding speed as needed using the split rudder speed brake. The rudder on the vertical tail wasn't just used for controlling yaw by deflecting left and right. It could split in two, deflecting outwards to a maximum of 62 degrees on either side. The gear is lowered as late as possible, and in the final moments before touching down, the commander will increase the angle of attack of the shuttle using the elevons in order to slow its descent rate before touching down. At the moment of main gear touchdown, the speed brake is commanded to fully open. At this point, the shuttle is still traveling at 360 km per hour, close to 0.3 Mach, and there is plenty of braking left to do. The runway at Cape Canaveral is 4.6 kilometers long, much longer than your average runway, with typical 3 kilometer long runways being able to deal with the heaviest of jumbo jets landing. As the nose gear touches down, the electro-hydraulic brakes in each of the 4 main landing gear wheels are fully engaged by application of the foot pedals in the cockpit. Each brake assembly had 9 carbon-lined beryllium discs, 4 rotors and 5 stators, which were pressed together to provide braking force. On STS-49, Bruce Melnick's mission, an additional braking mechanism was introduced, hidden away underneath the vertical tail speed brake, the drag chute. STS-49 was the maiden flight of both Endeavour and the drag chute, an explosively deployed parachute. You can even see the parachute door and sabot being flung from the back of the shuttle on landings. It was designed to allow the Space Shuttle to land on shorter 2,500 meter runways, a contingency plan in the event the Space Shuttle had to abort a launch and land on a runway on the other side of the Atlantic. For each and every launch, NASA sent staff to these predetermined landing locations, like Fairford RAF Base in Gloucestershire, England. A large team was needed to assist with the final moments of each Space Shuttle mission, and these teams were not once needed in the entire history of the Space Shuttle program. A giant fan was even rolled out on the runway to help disperse any toxic chemicals, like the hydrazine fuel, away from the shuttle and the crew. The mission is now over. The crew has disembarked and the Space Shuttle will be refurbished and flown back to Florida on the back of a 747 in preparation for its next mission.